Welcome to Thermodynamics lecture series. In the present video, we will discuss the application of first law of thermodynamics to a non-flow or closed system. Before going to discussion, first we will discuss the enthalpy. In thermodynamics, two important quantities are there. First one is the internal energy and second one is the pressure volume energy. Internal energy is the energy stored inside the system and represented by the small u, and pressure volume energy is the energy required to push the surroundings and create space for the fluid, and it is represented by the PV. So sum of these two energies is called as the enthalpy, which is represented by the small h. So enthalpy small h equal to the U plus PV. So let's see the meaning of enthalpy is enthalpy represents the total energy of a fluid during a thermodynamic process. So enthalpy is very useful in boilers, turbines, compressors, nozzles and heat exchangers because fluids in these devices flow continuously. Let's see the one example. Consider steam flowing through a pipe. So in this example, steam having the two energies. One is the internal energy small u, which means steam has internal energy because of its temperature. Second energy is the flow energy, which is the PV. Steam needs extra energy to push itself through the pipe against the pressure. So now enthalpy means total energy, which is the summation of internal energy plus flow energy, which means enthalpy small h equal to the U plus PV. Enthalpy of a fluid is the property of the fluid since it consists of the sum of the property and product of the two properties. So we know that one the U plus PV. So enthalpy is consist of the property internal energy and the product of the two properties, that is the P and V. Since enthalpy is a property like internal energy, pressure, specific volume and temperature, so enthalpy can be introduced into any problem, whether the process is a flow or non-flow process. Then let's see the total enthalpy of a mass small m of a fluid. Then total enthalpy we have to represented by the capital H, which is equal to the U plus PV, where total enthalpy we can be state that capital H equal to the small m into H, where the m is the mass of the fluid and H is the enthalpy. So let's see the enthalpy of a perfect gas. So enthalpy H equal to the U plus PV, and we know that when the internal energy of a perfect gas is the CVT, mCV delta T, where the m is the unit mass we are considering. So internal energy is the CVT, and we know that when the PV equal to the mRT, where m equal to the 1, then PV equal to the RT. Then for the perfect gas, enthalpy small h equal to the CV into T plus R into T. Then this can be, we can rewrite as the enthalpy H equal to the CV plus R into T. We know that one the relationship between the Cp and Cv. Cp minus Cv equal to the capital R. Then Cv plus R is the Cp. Then enthalpy H equal to the Cpt. Then total enthalpy will become the capital H equal to the mCpt. Next we will discuss the application of first law of thermodynamics to non-flow or closed system. First one is the reversible constant volume process, where the V equal to the constant. In a constant volume process, the gas is kept inside a rigid container. Since the container cannot expand or contract, so volume remains constant. Because the boundaries do not move, the system cannot do boundary work and no work is done on the system. Therefore, for a constant volume process, work done equal to the 0. And refer the figure which represents the system and states before and after the heat addition at a constant volume. So here I have to observe in the PV diagram. So where the volume is the constant, so state is changing from the one state to second state, then volume remains the constant, where the V1 equal to the V2. During the heat addition, pressure it will be increase, then it will be change, increase the pressure P1 to the P2. Considering the mass of the working substance as unity and applying the first law of thermodynamics to a constant volume process, and we know that one the first law of thermodynamics, which is the Q equal to the U2 minus U1 plus W. So, and we know that one the work done, which is equal to the W equal to integration of PdV, and in a constant volume process, this work done equal to the 0, which means, so integration of PdV equal to the 0 because of dV equal to the 0. Then, so if the work done equal to the 0, then based on the first law of thermodynamics, Q equal to the U2 minus U1, and we know that when the internal energy for the perfect gas is the Cv delta T, which is the Cv T2 minus T1. Here Cv is the specific heat at a constant volume. So for a mass m of a working substance, then Q equal to the U2 minus U1, which is equal to the mCv T2 minus T1. So remember this equation. For a constant volume process, Q equal to the U2 minus U1, which is equal to the mCv T2 minus T1. Let's see the second process, that is the reversible constant pressure process, where pressure equal to the constant, that is the P equal to the constant. In a constant pressure process, the pressure remains the same throughout the process. If the boundary of a system is fixed in the case of the constant volume process, the pressure increases when heat is added. But in a constant pressure process, the boundary must be free to move when heat is supplied. For example, consider a gas inside a cylinder with a movable piston. When heat is added to the gas expands and pushes the piston upward. Since the piston moves because of the force applied by the gas, and the gas does work on the surroundings. So let's see in the schematically. So it is the constant pressure process. Here gas is inside the cylinder and we are applying the heat addition, then so pressure is increases, then piston has to be moves to the upward. In this regard, pressure remains the constant. So piston is moving the upward, then so here does the work on the surroundings. So here also PV diagram also have to observe. So pressure is the same in the first state to second state, but volume is increases, that is the V1 to V2. So during a constant pressure process, heat is added to the system and gas expands and piston moves to the upward. So work is done by the gas on the surroundings. So okay, then we have to apply the first law of thermodynamics for the constant pressure process and considering the unit mass of the working substance. Then Q equal to the U2 minus U1 plus W. So then first we have to look for the work done W. We know that one the work done W equal to the integration of PdV. So here pressure is the constant and volume. So change in volume is the V2 minus V1. So work done which is equal to the P into V2 minus V1. Then so Q will become the U2 minus U1 plus P into V2 minus V1. So this equation we can be written as U2 minus U1 plus PV2 minus PV1. Then U2 plus PV2 minus of U1 plus PV1. We can be written as Q equal to the U2 plus PV2 minus of U1 plus PV1. And we know that one the enthalpy which is equal to the U plus PV. Then Q will become the, so this is the H2 and this is the H1. So Q equal to the H2 minus H1 which is equal to the, so mass we are considering the unit, then Cp into the T2 minus T1. So in a constant pressure process, Q equal to the H2 minus H1 which is equal to the Cp into T2 minus T1. So where the H equal to the enthalpy, that is the specific enthalpy. Then let consider the mass of the substance is small m. Then Q equal to the, so difference between the total enthalpy at the two states, that is the Q equal to the H2 minus H1 which is equal to the mCp T2 minus T1. So remember this equation. So in the constant pressure process, Q equal to the H2 minus H1 which is equal to the mCp T2 minus T1. Next we will discuss the third process, that is the isothermal process. So in the isothermal process, temperature T equal to the constant, then obviously PV equal to the MRT, then PV also constant. So in the isothermal process, PV equal to the constant and also T also constant. Here an isothermal process is a process in which the temperature remains constant throughout the process. So let's see how to maintain the temperature is the constant in the isothermal process. We know that one, when a gas inside a cylinder expands, then its temperature normally decreases. So to keep the constant temperature during the expansion, heat must be supplied continuously to the gas. Similarly, we know that when the gas is compressed, then its temperature tends to increase. Therefore, heat must be removed continuously to maintain constant temperature. So in isothermal process, temperature remains constant and heat is added during expansion and heat is removed during compression. So pressure and volume change during the process. So for isothermal process for an ideal gas, where the T equal to the constant, temperature is the constant, then PV equal to the MRT, then obviously PV also constant. So in the isothermal process, PV equal to the constant and T also constant. So this is the schematic representation of the isothermal process. So figure shows the system and states before and after heat addition at constant temperature. So in the PV diagram we have to observe. So state is changes from the 1 to 2. Then obviously volume is changes from the V1 to V2. And similarly pressure also changes from the P1 to the P2. And so this is the constant temperature process and the relation is the T equal to constant and PV also constant. So let considering the unit mass of working substance and applying the first law of thermodynamics to the process. And we know from the first law of thermodynamics, Q equal to the U2 minus U1 plus W. And we know that when the internal energy for the perfect gas, mCv dt, here we are considering the m equal to the unit mass, so m equal to the 1, and then dt is the, so T2 minus T1. Then Q equal to the Cv into T2 minus T1 plus W. So here this process is the isothermal process where the temperature is the constant. Then T2 equal to the T1. Then internal energy is the 0. So here Q can be written as the Q equal to the 0 plus W. So Q equal to the W. Then we have to calculate the work done W have to calculate. We know work done W equal to the integration of 1 to 2 P dV. So the process is the PV equal to the constant. So from this relation, we can be written as PV equal to the constant and P equal to the C by V. So you have to substitute this P equal to the C by V in the work done equation. Then work done W equal to the integration of 1 to 2 of the, so P is the C by V dV. So volume is changes from the V1 to V2. So then work done W equal to the integration of V1 to V2 C by V dV. So then this integration will become the, so constant C into the log of base E V. So V2 to V1. Then this relation will become the work done W equal to the C log base E V2 divided by V1. So then we know the relation PV equal to the constant. Then P1 V1 equal to the P2 V2 equal to the constant. So we know the work done equal to the C into log base E V2 divided by V1. So here C we can be written as P1 V1 or maybe P2 V2. If we considering the P1 V1, then W equal to the P1 V1 log of V2 by V1. If you considering the C equal to the P2 V2, then W equal to the P2 V2 log base E V2 by V1. So we know that when in the isothermal process, internal energy is the 0, then Q equal to the W, and relation is the P1 V1 log base E V2 divided by V1, which is equal to the P2 V2 log base E V2 divided by V1. So for mass M of the working substance, then so we can be written as this equation, Q equal to the W equal to the P1 V1, capital V1 is a total volume, not a specific volume. P1 V1 log base E V2 divided by V1, which is equal to the P2 V2 log base E V2 divided by V1. So we can be written as P1 V1 equal to the P2 V2, then V2 by V1 we can be written as V2 by V1 equal to the P1 by P2. So here I have to substitute, so V2 by V1 as the P1 by P2, then Q equal to the W equal to the P1 V1 log base E P1 divided by P2, which is equal to the P2 V2 log base E P1 by P2. So this is the isothermal process. Next we will discuss the fourth process, that is the reversible adiabatic process, where the PV relation is PV power gamma equal to the constant. An adiabatic process is a process in which no heat enters or leaves the fluid during the process, which means, so there is the Q equal to the 0. So the process may be reversible or irreversible, but in this section we are discussing about the reversible adiabatic process for a non-flow system. So then apply the first law of thermodynamics to the process, and based on the first law of thermodynamics, Q equal to the U2 minus U1 plus W. We know that when in the adiabatic process Q equal to the 0, then 0 equal to the U2 minus U1 plus W, and W equal to the U1 minus U2 for any adiabatic process, and let's consider this is the equation 1. So equation 1 is valid for all adiabatic process, whether the process is reversible or irreversible. During an adiabatic expansion, the fluid does work by using its own internal energy. As a result, the internal energy of the fluid is decreases. And moreover, during the adiabatic expansion, work is done on the fluid. This work increases the internal energy of the fluid. So for an adiabatic process to take place, the perfect thermal insulation for the system must be available. So let's see the relation, how it is the PV power gamma equal to the constant. So let's see, to derive the law PV power gamma equal to the constant. So to obtain the law defining P and V for the reversible adiabatic process, let us consider the non-flow energy equation in the differential form, that is the dq equal to the du plus dw. For a reversible process, dw equal to the pdv, then dq equal to the 0, which is equal to the du plus pdv. So du plus pdv equal to the 0, since the process is the adiabatic process where the q equal to the 0. And also we know that for the perfect gas, relation equal to the PV equal to the RT, or P equal to the RT divided by V. So then, we have to rewrite as du plus PdV equal to the 0. We know that the P equal to the RT divided by V. Then substitute, then this relation will become the du plus RT dV divided by V. So also we know that the du, internal energy, that is the CVT, or du equal to the CV dt. So we know that du is the CV dt and P is the RT by V. Then substituting in the equation of du plus PdV equal to the 0, then equation will become the CV dt plus RT dV by V equal to the 0. So next we have to dividing the both of the sides by the capital T, then we will get the CV dt divided by the T plus RT dV divided by T into V, where TT will be the cancel. Then this equation will become the CV dt divided by T plus RdV divided by V equal to the 0. So next we have to integrating in the both of this side. Then CV log base E capital T plus R log base E V equal to the constant. So we know that the T equal to the PV divided by R. So we know that for the perfect gas, PV equal to the MRT, where M equal to the 1. Then PV equal to the RT, then T equal to the PV by R. Then substituting that T equal to the PV by R, then this equation will become the CV log PV by R plus R into log V equal to the constant. So from this equation, dividing the CV from the both of these sides, then constant divided by CV, which is equal to the constant only. Then so CV will get be cancelled, and here also have to go for this CV. Then this equation will become the log base C PV divided by R plus R by CV log base C V equal to the constant. So and we know the relationship between the CV and the universal gas constant, that is the CV equal to the R divided by gamma minus 1. So from this relation we can be rewrite as R divided by CV equal to the gamma minus 1. So in this equation already we are having the R by CV, then substitute gamma minus 1. Then this equation will become the log base C PV by R plus gamma minus 1 into log base C V equal to the constant. So next we can rewrite this equation. So log base E PV divided by R plus log base E V to the power gamma minus 1 equal to the constant. So this equation we can be rewrite as log base E PV into V to the power gamma minus 1 divided by capital R equal to the constant. Here V and V to the power minus 1 will get the cancel. Then log base E PV power gamma divided by R equal to the constant, and PV power gamma divided by R, which is equal to the e to the power constant, which is equal to the constant. Then we can be state that PV power gamma equal to the constant. So in the reversible adiabatic process, we have to following the law is the PV power gamma equal to the constant. So next we have to look for the expansion for work W in the reversible adiabatic process. A reversible adiabatic process for a perfect gas is shown on a PV diagram in the figure. So in the figure you have to see, so this is the schematic representation of the adiabatic process where you have to observe the PV diagram. So here volume is changes from the V1 to V2 and pressure is changes from the P1 to P2, and this shaded area is the work done during the adiabatic process, and relation between the P and V is the PV power gamma equal to the constant. Then work done is given by shaded area, and this area can be evaluated by integration, that is the work done W equal to the integration of V2 to V1 P dV. The relation is PV power gamma equal to the constant, let's consider C. So PV power gamma equal to the C. Then we have to substitute here P value, where we know that one PV power gamma equal to the constant, then P equal to the C divided by V power gamma. Then work done W will become the integration of V2 to V1 of C dV divided by V power gamma. So here C is the constant, then taken the outside from the integration, then work done W equal to the C into integration of V2 to V1. So 1 divided by V power gamma, which is equal to the V to the power minus gamma dV. Then this integration will become the C into V to the power minus gamma plus 1 divided by minus gamma plus 1 limits of V2 to V1. Then final W equal to the C into V to the power 1 minus gamma minus V1 to the power 1 minus gamma divided by 1 minus gamma. So then work done W equal to the C into V1 to the power 1 minus gamma minus V2 to the power 1 minus gamma divided by gamma minus 1. So the constant is the, in this equation, we can be written as constant is, we know PV power gamma equal to the constant C, that is the, we can be rewrite as P1 V1 power gamma equal to the C, which is equal to the P2 V2 power gamma. So the constant in this equation can be written as P1 V1 power gamma or P2 V2 power gamma. Then substitute, then work done W will become the, so P1 V1 power gamma into V1 to the power 1 minus gamma minus of P2 V2 to the power gamma into V2 power 1 minus 1 divided by gamma minus 1. So the finally we can be rewrite as W equal to the P1 V1 minus P2 V2 divided by gamma minus 1. So work done in the adiabatic process is the P1 V1 minus P2 V2 divided by gamma minus 1. So this can be, we can rewrite as, we know PV equal to the RT, then W equal to the, so R T1 minus T2 divided by gamma minus 1. So next we have to see the relationship between the T and V and T and P in the adiabatic process. So we know the perfect gas relation, that is the PV equal to the RT. Then we have to see the relationship between the adiabatic process. So in general for the perfect gas PV equal to the RT and P equal to the RT divided by V. So then we have to putting this value in the PV power gamma constant, then RT divided by V into V to the power gamma equal to the constant, then T into V to the power gamma minus 1 equal to the constant. So this is the relationship between the T and V. Similarly, I have to look for the relationship between the T and P. So where PV equal to the RT and V equal to RT divided by P. Then I have to substitute V value in the PV power gamma equal to the constant. Then P into RT divided by P to the power gamma equal to the constant. Then, so R to the power gamma divided by P to the power gamma minus 1, where R is the constant. So, T to the power R divided by P to the power gamma minus 1 equal to the constant. So, this we can be rewrite as T divided by P to the power gamma minus 1 divided by gamma equal to the constant. So, this is the relationship between the T and P in the adiabatic process. So, next we have to look for the fifth one, that is the polytropic reversible process. So, where the PV power n equal to the constant. It is found that many processes in practice approximate to a reversible law of form PV power n equal to the constant, where n is the constant. So, in general, both vapors and perfect gases obeys this type of law closely in many non-flow processes. So, such processes are internally reversible. So, and we know that when for any reversible process, work done W equal to the integration of PdV, and for the polytropic process, relation between the P and V is the PV power n equal to the C. Then we can be written as P equal to the C divided by V to the power n, where C is the constant. Then substitute this P equal to the C by V power n. Then work done W equal to the C integration of V2 to the V1 dV divided by V to the power n. So next we have to integrate this one. Then we will get the work done W equal to the C into V1 to the power minus n plus 1 minus of V2 to the power minus n plus 1 divided by n minus 1. So we know that when the C is the constant, where the PVN equal to the constant, and this can be written as P1 V1 power n equal to the P2 V2 power n equal to the constant. So I have to substitute this C as the P1 V1 power n or P2 V2 power n. Then work done equation will become the P1 V1 minus P2 V2 divided by n minus 1. So this we can be rewrite as work done W equal to the R into T1 minus T2 divided by n minus 1. So we have to look for the relationship between the T and V and T and P for the polytropic process. So this is a relation. So that is the T2 by T1, which is equal to the V1 by V2 whole to the power of n minus 1. So this is the relationship between the T and V. And similarly for the T and P is the T2 divided by T1, which is equal to the P2 divided by P1 whole to the power n minus 1 divided by n. So next we have to look for the heat transfer during polytropic process for a perfect gas, which is the relation is the PV equal to the RT. And we have to apply the first law of thermodynamics to the process, and we know the Q equal to the U2 minus U1 plus W. And we know internal energy U2 minus U1 for the perfect gas is the CV into T2 minus T1. Then heat transfer Q equal to the CV into T2 minus T1 plus we know the work done, which is the R into T1 minus T2 divided by n minus 1. So this equation we can be rewrite as Q equal to the R into T1 minus T2 divided by n minus 1 minus CV into T1 minus T2. So we know the relation between the CV and the R, that is the CV equal to the R divided by gamma minus 1. Then you have to substitute this CV value as the R divided by gamma minus 1. Then Q will become the Q equal to the R divided by n minus 1 into T1 minus T2 minus R divided by gamma minus 1 into T1 minus T2. Here R into T1 minus T2 is the common one. Then we have to take the outside. Then Q equal to the R into T1 minus T2 into 1 divided by n minus 1 minus 1 divided by gamma minus 1. So from this one we can be rewrite as Q equal to the R into T1 minus T2 gamma minus n divided by gamma minus 1 into n minus 1. So finally, so we can be rewrite as heat transfer in the polytropic process Q equal to the gamma minus n into R into T1 minus T2 divided by gamma minus 1 into n minus 1. So and also we can be rewrite as the relationship between the work done and the heat transfer, that is the Q equal to the gamma minus n divided by gamma minus 1 into the work done. So this is the polytropic process. In a polytropic process, the index small n depends on the amount of heat transfer and work interaction during the process. In this regard, many thermodynamic processes are actually special cases of the polytropic process for a perfect gas. So let's see. So let's consider, first we have to considering the first special case of the polytropic process. We know that when in the polytropic process the relation is the PV power n equal to the constant. So here we are considering the when n equal to the 0. So when the n equal to the 0, then PV to the power 0 equal to the constant, then P equal to the constant. So this process is the constant pressure process or the isobaric process. So in the polytropic process, when the n equal to the 0, the process is the constant pressure process. Similarly, when the n equal to the infinity, then PV to the power infinity equal to the constant, then V equal to the constant. So special case, second special case is the when n equal to the infinity, the process will become the constant volume process or the isochoric process. Similarly, when the n equal to the 1, then when n equal to the 1, then PV equal to the constant. Then for the perfect gas, we know that when the PV equal to the RT, then T also constant. So when the n equal to 1 in the polytropic process, the process will become the isothermal or constant temperature process. Similarly, when the n equal to the gamma, then the process will become the, so PV power gamma equal to the constant, and this process is the reversible adiabatic process. So let observe the PV diagram for the special cases of the polytropic process. Here state 1 to state A represents the constant pressure process where the n equal to 0, and 1 to A is the constant pressure cooling, and 1 to A dash is the constant pressure heating. So next we have to look for the 1 to B. So in the 1 to B, where the index n equal to the 1. So we know that when the index 1 is equal to the 1, this process is the isothermal process. Here 1 to B is the isothermal compression, and 1 to B dash is the isothermal expansion. So next we have to look for the state 1 to C. So where the n equal to the gamma, and we know that when n equal to the gamma, the process is the adiabatic process. Here 1 to C is the adiabatic compression, and 1 to C dash is the adiabatic expansion. And last one, have to observe the process 1 to D and the 1 to D dash, where the n equal to the infinity. So where the n equal to the infinity, the process is the constant volume process. Here 1 to D is the constant volume process at the heating, and so 1 to D dash is the constant volume process in the cooling. And here this table represents the summarization of the all the process. So next we will discuss the free expansion. The expansion of a gas against vacuum is known as free expansion, and it is also called as the unrestrained expansion. So in the free expansion, the gas expands into a vacuum, so there is no external resistance offered to the gas. Therefore, the work done during free expansion is 0. And moreover, since the process is usually takes place in an insulated system, so heat transfer is also 0. So work done is 0 and moreover, so heat transfer also the 0. Then I have to apply the first law of thermodynamics, that is the Q equal to the delta U plus W, where Q is the 0 and W also 0. Then delta U also will be 0. Then for the free expansion process, no work transfer occur, no heat transfer occur, and moreover, change in internal energy is 0. So for a perfect gas, we know that when the internal energy is the CVT, then in the free expansion process, so temperature is the remains constant during the free expansion of ideal gas.